Over the last couple of months, NATO has reported a sharp rise in Russian efforts to jam satellites across the UK, Germany, Sweden, and across the Baltic and Red Seas. Interfering with military operations relying on these satellites can be a real threat to security and civilian safety. Now, laser communication could provide a deployable solution to the front lines. Unlike radio frequency links, laser terminals use narrowly focused optical beams that are difficult to jam or intercept, even in contested environments. Astrolight is a Lithuanian space and defense company with tried and tested terminals already in use by NATO. Dalius Petrulionis is the co-founder and CTO of Astrolight, with more than a decade of experience designing and developing high-power, ultra-short pulse lasers. In our conversation, Petrulionis discusses how lasers are advancing communication technology and the real-world turmoil that is driving demand for these systems.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Dalius, thank you so much for giving us the time to talk about these advancing communication systems.
Yeah, no problem. I'm happy to have the chat.
Well, optical and quantum communication technologies have been described as a revolution in SATCOMs. Can you tell me what is the demand that is driving the advancements in this field?
So I think we have to separate kind of classical and quantum optical communication because they are both optical. With classical communication, I think there is much clearer demand, and that demand is driven by both commercial and governmental demand. Commercial because it really is important now to transmit large amounts of data with low latency in space. We see that with SpaceX projects, many other projects as well, but also smaller kind of very high volume data applications like Earth observation, where people are generating a lot of data that they need to get on the ground because it's fine and good to have data transmission in space. People live on the ground. We do everything on the ground. So that data has to come down somehow. And with governmental, there is the benefit, of course, of security, it being hard to jam. So that's kind of the classical angle where the data rate is much faster than radio, and that's the driving angle. With quantum, of course, there are concerns over security, and China has been quite good in that regard. However, I think the demand in terms of commercial demand is not there yet. It's driven by this kind of future proofing of reliable, hard to kind of intercept communication systems.
And some exciting news I just saw too. Astrolight announcing the deployment of its first Arctic ground station for laser satellite communications in Greenland. Tell me about the technology at the center of this and how far along is this project today?
Yeah, so this project has been in the making for quite some time. So the ground station is, of course, based on our own technology built by Astrolight. And we kind of aim as a company to first build the technology, but then expand into the use of that technology as a business model. So we aim to provide a service of data downlink to commercial or governmental customers, whatever is needed, where they could use our ground stations and our ground station network to do that. And it's a big chicken and egg problem because it's really not a lot of terminals in space yet, not a lot of terminals on the ground. So for the user who wants to take advantage of this technology, it's really unclear how they're going to do it. So we've been supported in this by European Space Agency in building this ground station, which kind of would be the first of the pilots that we are doing where we will prove that this works, because this technology in terms of space to space is proven. In terms of space to ground, much less so because of the atmosphere. And from there, we can also start providing commercial service with more and more ground stations in different regions. We have, for example, some projects going on in Greece. Maybe there will be one ground station there. So we will see.
Very exciting. And turning now, talking about Atlas 2, a laser communication terminal for space to ground and space to space links. What can you tell me about the lasers at work here that are kind of helping this run?
So we build our own lasers. Astrolight is a very vertically integrated company. And touching a little bit on your previous question, I said that all of that technology is ours, and it includes the laser, it includes the feedback system, the optics, the mechanics, everything basically. And while that ground station builds on our previous kind of deliveries in ground station segment, Atlas has been delivered to 3 customers already, and it's our own laser there. We build it basically from scratch using the expertise that is available in Lithuania, which is pretty well known for lasers. Not maybe so much for fiber lasers, which Atlas is using, but there is a significant infrastructure that we can leverage, and that's why we do it ourselves.
Exciting. And talking a little bit more about the need for this, and security certainly is something that comes to mind. uh we have existing ways to communicate, but they're kind of turning out to be flawed in a lot of ways. So how do laser communication systems compare to the current standards like radio or satellite based GPS?
So I touched upon this in the beginning where I said that it's much faster and that's driving commercial demand. That's basically it. So lasers in space are fiber without the fiber. So it's something that is analogous to replacing your kind of dial up connection with a fiber connection. So orders of magnitude improvement. And that's the main advantage. However, all of the technologies have their own drawbacks. So, of course, lasers rely on kind of visual line of sight, which means that they don't work through clouds. That's where the ground station network comes in. So, some of the ground stations will not have clouds. Satellite flies around Earth in low Earth orbit in uh, a little bit more than an hour. So, it's going to see many ground stations, and there will be many opportunities for downlink. So I see those technologies as complementary. So even now, people are placing 2 radio transmitters on satellites: one very reliable, low frequency, low data rate, and one very high frequency, less reliable, but very high data rate terminal. So we see this technology replacing that high data rate terminal with an even higher data rate terminal using optical.
Exciting. And is there a kind of a marriage between the two? Lasers can do a lot of things better than current systems, but is there a kind of a marriage between, we don't totally give up on the radio systems or the satellite, but if we join these all together, we have something more high speed, more secure, maybe?
Definitely. So as I said, we will not give up radio completely. That would not make sense. However, for this low latency or very high throughput connection, there is no way that radio can provide 100 gigabits per second while allowing everybody to use the spectrum, which is finite, which is a finite resource. I mean, you have to license the spectrum, and if somebody is using it, you can't use it. That's different from laser, because laser will give you a 50, 100 meter spot on the ground from orbit, which will not interfere with anything else. So there's no licensing required.
And today we always want everything faster. We have more data to transfer, and we want to do it quicker. Um, can you give me kind of the specific applications you can see these Astrolight systems being used for, and maybe talk about who is turning to use them? We talked about security. Is this something that we can expect defense departments to use? And kind of talk to me about the specific uses you can see this system really helping advance.
So first of all, it's Earth observation. Earth observation, especially hyperspectral synthetic aperture radar, generates lots and lots of data, and you have a hard time actually compressing all that data in a lossless way in orbit. So what you want to do is you want to get everything down so you can sift through it, and that's something that will bottleneck current radio communications, but will be enabled by lasers. And especially as satellites proliferate, those licensing and spectrum requirements that would choke radio communications will allow lasers to continue working. However, there is also, it's good that you mentioned defense applications, because as I mentioned, the spot on the ground is small. It's very hard to kind of intercept it. It's not radio, which goes everywhere. And we do have products also for naval applications, for example, ship-to-ship applications, where the inability to jam the beam using conventional electronic warfare equipment, or inability even to see the beam in most circumstances, is something that's very, very advantageous.
Yeah, and talking too about the jamming, we've seen in the news, recently, Russia jamming NATO satellites. We've seen instances where GPS shows one nation, your ship is in the inland somewhere, something that doesn't make sense. So GPS signals can not only be jammed, but they can be spoofed to be, whether intentional or just scrambled randomly to give a false reading there. Is this something that laser communication terminals from Astrolight can offer a solution to these issues?
Well, first of all, it's a medium for communication that is hard to jam. Of course, positioning is a bit of a different matter, but we are working on that as well. So the naval terminal can actually be used to position yourself or your counterpart in a kind of radio denied, GNSS denied environment. And that kind of mirrors how some RF systems work, where they have a very tight RF beam and they use that beam to basically scan over the counterpart and see how far off the line of communication it is, and give you in polar coordinates basically the distance and the angular range where you expect your counterpart to be. However, lasers are much more precise for this, both as distance measurement device, as in LiDAR, but also in terms of divergence, in terms of how precise your angle is. So this can totally replace basically GNSS-based navigation in some applications, like, for example, for a remote drone that you have communication with.
Very exciting too, because when we talk about accurate readings, we're talking about situations too, in defense where this is potentially life-saving information, right? Like you need to know where your teams are and everything like that. So, the applications here really can make an impact that can be felt, through those people that are, life or death relying on that information.
Yeah, definitely. And it's something that is unique to this laser thing because it's so narrow of a beam.
Mm. And we talked a little bit about the bottlenecks, and certainly it's never easy when you're in, on the cusp with an emerging technology, right? You don't have the infrastructure set up for everything else. We talked about the satellites. Are those all the bottlenecks and challenges facing, laser communication, or is there more that is, right now keeping it from reaching its full potential?
So I would say there are kind of three bottlenecks. One is physical, where the laser has to go in the end through atmosphere. And that's going to be your scintillation, your rain, your fog, which is hard to get through. We actually demonstrated operation in light fog and rain during the REPMUS exercise in Portugal, where we connected ship to another ship using our device as a basically network bridge. But this is still kind of a concern for people. And that's another barrier. Demonstrating that it works and works reliably is difficult because people always come up with questions in terms of kind of satellite communication. It's always a question about clouds. I have to explain that, okay, statistically, you are going to have a very hard time finding a situation where every ground station that your satellite can see is covered by clouds. And when communicating, let's say, ship to ship, people would kind of point fingers and say, okay, I don't see the ship, can you communicate? And I would go like, yes, okay, look, the communication is ongoing. So there's a lot of kind of perception to this as well. And of course there is the engineering barrier, which is you actually have to make it work, and that's what we are trying to do so far, somewhat successfully.
Great, great. It sounds like there's some cooling of some people getting overexcited. Oh, a cloud will stop this. Well, sure, but if you have several terminals, the whole sky is not going to be covered in cloud. It's not as it's a challenge that can be easily overcome, I guess. So that you need to kind of cool those people down so they can understand that better, right?
Yeah, so I would be more reserved than saying easily, but it can be overcome. And this is for satellites. There's also the chicken and egg problem, like with any new technology, which requires kind of two counterparts. This was the same with high frequency radio as well for satellites, where people are reluctant to move to a technology that is less proven and requires infrastructure, specific infrastructure on the ground, which means there's a lot of costs. And that's why we are solving both ends. We are solving the satellite end and the ground as well, so that the customer has an easier time starting to use this technology.
Great. And this is always a $1 million question with no easy answer, but I always like to ask it to get the insight. Where do you see this technology in, say, 10 years? And what does this mean for the future of radio and other systems that it could, replace in some ways, but maybe would be better served to work kind of symbiotically with them?
I think any system is much more resilient if it has multiple paths to achieve the same thing. And I think for satellites, resiliency is very important. So I see this being as one of the tools in the toolbox of a satellite operator or a ship operator in terms of kind of defense applications, where they have this unique capability sometimes that is not enabled by radio, by staying silent, or by having this huge data rate. But in 10 years, I think there are some pretty obvious applications emerging. So deep space communication at high speed is only possible through optical. That's not a question. Everything RF is going to be slow. That's just basic physics. Same goes for satellite to satellite communication because the distances are large. And I think the same goes, and this is a bit more controversial, but I do believe that the same goes for satellite to ground when data volumes increase and the numbers of satellites increase, because the radio spectrum will not be able to support that data volume, which is required for the kind of modern satellite constellation. And there's not going to be one of them. Everybody now wants to have their own sovereign capability, so there will be multiple. And you heard when SpaceX used radio link in a kind of reverse way, where they try to transmit on the receive channel or receive on the transmit, I think that was quite a big news story. So this is something that is solved by this. And this is, I think, one of the first indications that this is going to be the case in 10 years, that most people will use optical communication for their high volume data links. And I think for defense applications as well, it is inherently harder to jam. It's not just the cat and mouse game where you change some frequency and then the enemy changes the frequency and then you change the frequency again. You have to be within the line of communication to jam it. It's not sensitive to anything you throw at it from the side. So this will be a component for stuff like you have these loyal wingman programs, for example, popping up, which complement stealth fighters with stealth drones. You can't really use radio to transmit those huge amounts of data for battlefield awareness gathered by the drones. You will have to use optical, and that's direct line of sight. It's in clear skies. So those are, I think, the directions it will go in 10 years.
Yeah, nothing drives advancements more like an interest from defense, right? That was so pressing.
Yeah.
Really excited to see where it goes. And I know you said Astrolight's kind of working with the chicken and the egg, to get those things going. So please just keep us updated on those developments and we'll be watching closely. But thank you so much for giving us the time and talking today.
Yeah, thank you for having me. It was a pleasure.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.